Okay, so for today, we're gonna go through chemical formulas, chemical equations, and more. Quite a fair bit to cover. We're going through pretty quickly, but do let me know midway if you feel that I'm going a bit too fast. Right now, you should be able to see the share screen of the textbook. This is actually on page 87. So I'll be actually picking up segments of the textbook, okay, to refer to it. So as you have your textbook with you, you can actually write down all the little notes and stuff on your textbook. Okay, so let's start. Okay, so let's start with chemical formulas. We're gonna do chemical formulas of ionic compounds first. Okay, then we're gonna look at later chemical formulas of elements. Okay, why we talk about chemical formulas first is really because so we're gonna start with chemical formulas. Okay, it's really because from the chemical formula, only when we know how to go about writing the chemical formulas, we can actually do the chemical equations. Now, once we're able to do chemical equations, okay, then we can really look at the idea of chemical calculations. Okay, chemical calculations is the one where all of you are referring to as the mole calculations. Okay, so these are the few, this is the sequence that we'll be going through from chemical formulas to chemical equations to chemical calculations. Okay, why is it in this sequence? It's really because for us to really know how to do chemical calculations, you really need to know what chemical equations really means. Once you know the chemical equation, what they really means, okay, this really is built upon the basis of knowing what the chemical formulas are. Okay, so this is really the what we're going through today. So in the textbook, we'll be going through how to find the chemical formulas for ionic compounds. Actually, to be exact, it's not really focusing on ionic only, but more of really how to determine the chemical formula of compounds. Then we'll also be looking at how to determine chemical formulas of elements. Okay, so let's start off with this part over here first. So textbook, let's refer to page 87. Okay, so let's start with compounds first. Okay, so generally, let's start off with the naming. So in terms of naming, I think most of you are very familiar with names. So, but first thing I want to highlight is that compounds that are made from two elements, they will end with the idea of IDE. So sodium chloride, obviously you see there's the IDE there. So this is actually made of sodium and chlorine, two elements only. Zinc oxide and with IDE, so this is made of two elements only, and most of us know is zinc and oxygen. Carbon dioxide, carbon and oxygen. Okay, we know that dioxide, the word oxide actually tells you that it's bonded with oxygen. So once the compound name ends with IDE, you will know that it's made out of only two elements. Okay, so two element compounds, that's how you generally name them. Okay, the other naming that you will tend to see is really based on these two. Okay, first one is hydroxide. So example, potassium hydroxide. This consists of potassium and hydroxide ions. So the first ion I need to remember, okay, is actually hydroxide ions. So what are exactly hydroxide ions? They're actually OH minus ions. Okay, OH minus. So whenever you see hydroxide, you will need to recap, it is OH minus. Compound that contains a negatively charged polyatomic ion. Polyatomic means more than one atom. Okay, so a compound that contains a negatively charged polyatomic ion containing oxygen usually has a name ending with ATE. So what are the few classic examples is actually sulfate. Sulfate consists of four oxygen and one sulfate ion. Example SO4 2 minus. Next one is nitrate. So you can see it ends with ATE, means it contains oxygen also. This is the one which we know is NO3 minus. Last one is carbonate. So carbon with oxygen, CO3 2 minus. So you realize sulfate is sulfur plus oxygen. That's why it's SO4 2 minus. Nitrate is nitrogen. Because of the ATE, you know, it has oxygen with it also. So NO3 minus. Carbonate, CO3 2 minus. So the four polyatomic ions that I need to remember is OH minus, SO4 2 minus, NO3 minus, and CO3 2 minus. Okay, so most of your compounds you either see ending with IDE, or you will see it ending with hydroxide, or you will see it ending with something like ATE, sulfate, nitrate, or carbonate. So these are the various naming of the compounds. Okay, now once we know how the compounds are named, okay, let's look at some general rules of writing chemical formulas which we are familiar with, but we just go through a little bit. Okay, for many compounds that contains both metallic and non-metallic elements, that means metal and non-metal, we will tend to write the symbol of the metallic element first. So example, calcium oxide is made of calcium and oxygen. We will always have the metal name coming first. Okay, next, sodium chloride, NaCl. Sodium is a metal, so we always have the metal name coming first. Same like magnesium carbonate, magnesium is the metal, so the magnesium name will come first. Okay, so that's the first rule. The second rule is this, okay, the number of atoms is written as a subscript. Subscript means it's a very small number at the bottom right, okay, to the right of the atom symbol. So this one most of us are familiar with. Example, MgCO3 means I got one Mg, one carbon, and three oxygen. Okay, so this is the way to write it. Now, so you don't write a big tree like this, okay? And because when I want three oxygen, I don't write the tree in front of the O, it must always be behind the O. So like that is the way to write in terms of the number of atoms, how many you want to indicate. Third rule, the subscripts are the simplest set of whole numbers. What do I mean? For example, calcium oxide is CaO. Whenever you see like Ca2O2, can you see the ratio is 2 is to 2? This is not a simplest ratio because 2 is to 2 can be, 2 is to 2 can be always simplified into 1 is to 1. Okay, so all the subscript is always simplified to the lowest ratio. Fourth point, okay, fourth point, what do we have? Is actually that, which I mentioned before, it is not necessary to write the subscript 1. So for example, sodium chloride is Na1Cl1 to say it's made of one sodium atom, one chlorine atom bonded together. But whenever you got one like this, we will actually not write it down. So our formula is NaCl. Okay. Lastly, if the compound contains more than one polyatomic ion, the formula of the ion is placed within a bracket. So for example, copper 2 hydroxide consists of one Cu2 plus ion and two OH minus ion. So how to show that it contains two OH minus ions? I need to place the OH in a bracket. Okay, so polyatomic ions, you need to place it in the bracket in order for you to show that it is two of it. So take note, polyatomic ions, you need to make sure that the formula is placed within brackets. Okay, if you got more than one of it. So these are the few rules. Okay, I'm not sure how many of you are familiar with this page. Okay, but these are the rules actually you have been doing as you are going through. Okay, these are the rules that you have been doing as you're going through writing chemical formulas. Okay, so how do you exactly determine the chemical formulas of ionic compounds? This is actually a thing that we have always been trying to do. It's over here. All the positive charges must be equals to all the negative charges in the compound. For example, okay, let's look at this. Ca2 plus. So the total positive charge is plus 2. Cl minus. Okay, if I only got one of this, the total negative charge is minus 1. So it's not balanced. So what I need is I need 2Cl, so minus 1 over here, minus 1 over here, so that the total negative charge is minus 2. Can you see plus 2, minus 2? The positive charge is balanced with the negative charge. That's why the formula for calcium chloride is actually CaCl2. So that your 2 plus balanced out by a 2 times minus 1. Okay? So this is the reason why, okay, this is the reason why the formula is CaCl2. It's really to balance the positive and the negative charges. This is the concept behind it. But of course, you don't really go and think of balancing it all the time. Most of the time, when we're doing chemical formulas, we tend to do what we call this crisscross method. Right? So to do the crisscross method, okay, or to do the crossover method, okay, is actually to find the formula. First, you write down the ions with the charges. Okay, so then it'll be like this. After that, we will cross the numbers over. Okay, we'll cross the numbers over without the charge. So before we go into writing all the chemical formulas, I want us to look at your periodic table. I want to zoom in a little bit. Okay, in your periodic table, whenever you receive it, so this is something that you will get in your, all your papers, you always receive the periodic table. So whenever you get a periodic table, please don't start doing your papers immediately. Go into questions. I want you to always, when you have the periodic table, write this number down. Okay, I'm going to use red to just show it's important. This is actually group number. So we got group 1, 2, 3, 4, 5, 6, 7, 0. Okay, above each of the group number, I want you to write what I call the bonding number. Okay, so above group 1, you write 1. Above group 2, you write 2. Group 3, you write 3. Group 4, you write 4. Group 5, you write 3. Group 6, you write 2. Group 7, you write 1. Group 8, you write 0. Or group 0, write 0. So it's always a 1, 2, 3, 4, 3, 2, 1, 0. These numbers are very important whenever you are doing chemical formulas because they will help you to get your chemical formulas. Okay, so this periodic table with the top here, every time make sure when you get your periodic table in your question papers and stuff, you're writing all this down. Okay, let's go back here. So how exactly you do the chemical formulas? So first example that they give is aluminum oxide. So you can see Al is 3 plus and O2 minus. Now, generally, I don't like to write the plus and the minus. So if I base it on my periodic table, aluminum is over here. So aluminum, the bonding number is 3. So I'll go back here. Aluminum, bonding number is 3. Oxygen is over here. Bonding number is 2. So I'll go and write O and 2 over here. So you realize the bonding number always goes to the top right-hand corner. Now, whatever I've written here is not the chemical formulas. The chemical formula will only, you have only come up with the chemical formulas only after you have crisscrossed the numbers. Okay, so cross over the numbers, take the 2, cross over to the bottom right of aluminium, take the 3 of aluminium, cross over to the bottom right of oxygen. What you're going to get is Al2O3. Okay, so this is how you get the chemical formula for aluminum oxide. Now, before we go into magnesium oxide and stuff, I want us to try another one. So let's go to the blank notes. Okay, I'm going to give you another example. So what we can try is maybe aluminium chloride. Okay, aluminium chloride. Maybe not chloride. Let's try aluminium fluoride. Okay, aluminium fluoride. Now let's zoom in a little bit. So aluminium fluoride, what would be the chemical formula? So first thing, go back to your periodic table, check. Aluminium, bonding number 3. So let's write down aluminium, bonding number 3. Fluoride is actually fluorine. Fluorine is over here. Bonding number is 1. So I'm going to write F1. So next, this is not the chemical formula. I need to cross over first, then I can get the chemical formula. So once I cross over, I'm going to get Al1F3. So this is the chemical formula. But some of you must be thinking, I thought you said, right, previously that we will never write 1 in chemistry. Where did you hear that from? Yeah, from me. But then, right, if you were to go back to the things that I've gone through just now, what do you realize? Rule number 4, it says it is not necessary to write the subscript 1. So coming back here, this is a subscript 1. So actually I can cancel it out. What I'm going to get is ALF3. Okay, so this is how you get the chemical formula, okay, for compounds. Really use the bonding number, cross them over, then you will get the chemical formula. Okay, going back to this, let's look at the next example. What's the chemical formula for magnesium oxide? So magnesium oxide is made out of magnesium and oxygen. So what we're gonna do, take magnesium and oxygen, find out what's their bonding number. So going back here, magnesium is here, bonding number is 2. Oxygen is here, bonding number is also 2. So bonding number is 2 for both of them. You cross over, you're gonna get Mg2O2. So which is what they got over here. Now, why we don't see the formula Mg2O2? Instead, we tend to see MgO. It's really because we will always simplify to lowest ratio. Okay, simplify to the lowest ratio. So Mg2O2 is actually 2 magnesium is to 2 oxygen. This is not the simplest ratio. As such, we need to convert it 1 is to 1, okay, which is actually MgO. 1 is to 1. 1 magnesium is to 1 oxygen. Okay, so this is a second step in terms, second example in terms of chemical formulas. Okay, now let's do a little bit where it gets a bit more chim, okay, because we're gonna deal with what we call the polyatomic ions. Polyatomic ions. So what exactly are polyatomic ions? It is where the ions constitute more than one atom. So OH minus is actually 2 atoms combining together to form the ion. Okay, another classic example of polyatomic ion is NH4 plus. Right? NH4 plus is actually made of 1N and 4H together. This whole thing here together form an ion. Same thing, SO4 2 minus, 1S4O come together to form an ion. So all these that I've circled so far are what we call the polyatomic ions. So let's start simple first. Let's go with CuOH minus, Cu2 plus and OH minus. So copper we know is 2 plus. Okay, later on I'll give you a page to let you see how I know that. But copper is 2 plus. So the bonding number for copper, if it is 2 plus, the bonding number is actually 2. So you literally just take the charge up there. That is actually the bonding number. OH minus, okay, I want you to do a circle like this and write OH inside. So this will help you to remember that actually the OH is together all the time. I cannot suddenly change from OH to O2H, O2H, or change to OH2. This is not hydroxide. This is not hydroxide. You are actually, when you write these kind of things, you're actually changing the ion itself. It's no longer called hydroxide. It's called some other thing really. So, cannot. So think of it as whenever you say hydroxide, it must be OH only. Then because it's a minus, minus stands for 1 minus. So I put a bonding number here as 1. So Cu2, Cu with a bonding number 2, OH with a bonding number 1. Then I cross over. What I'm going to get is CuOH2. This circle here, we're going to simplify it using a bracket. So when we simplify it, you get Cu bracket OH2. Okay, so this is the chemical formula for copper hydroxide. Okay, so using crisscross, you can see how the polyatomic ions will work out. Now let's go on to the next one. Okay, ammonium sulfate. This is actually ammonium sulfate, ammonium sulfate. So it's made out of the ammonium ion, NH4 plus. Sulfate ion is SO4 2 minus. So I'm going to try to combine these two to form a compound. So the example is here, but remember I don't like to see this plus and the minus, right? So because I know it's NH4, I know it's a polyatomic ion, I'll circle this whole thing. Plus just means 1 plus. So I'll put a 1 there, the bonding number is 1. So if you see plus, the bonding number is 1. You see minus, the bonding number is also 1. So just take note of that. SO4 2 minus, so SO4 clustered together. 2 minus just means the bonding number is 2. Then we will cross over. What you're going to get is NH4 2, SO4 1. So if it is a 1, we can actually don't even write it down. Once there's no numbers outside, we can just erase the whole bracket. So the formula actually looks like this, but obviously you don't see a big circle in your chemical formulas, right? This big circle actually represents your bracket. So my formula, I'm going to simplify it to NH4 bracket 2SO4. Okay, so this is the chemical formula for ammonium sulfate. Again, this is the chemical formula for ammonium sulfate. Okay, once able to do all this, I think it's generally quite okay already. So let's try another example. Okay, let's try ammonium carbonate. Okay, ammonium carbonate. So how exactly to write the chemical formula for ammonium carbonate? So ammonium is NH4. Okay, sorry, let me not write that. It's NH4 plus. Carbonate is CO3 2 minus. So we can't crisscross like that because you realize I don't always write the plus and the minus sign. So I must first convert this into NH4. Because it's a polyatomic ion, I'll draw this circle like this. Plus means the bonding number is 1. CO3 2 minus, okay, means that I got CO3 clustered together. The bonding number is 2. Right? The bonding number is 2. So once I've gotten the circles properly and the bonding number properly, I can now do my crisscross. So I'm going to get NH4, 2 of them, CO3, 1 of it. So as we remember, whenever there's only one of it, we don't write the number 1. Because this big circle here outside got no number, right? You just take it as 1, right? So I don't need to draw this big circle also. So once I've gotten this, I will just convert this into the regular formula that we tend to see. It's NH4 bracket 2, because this circle represents bracket, CO3. So this is actually ammonium carbonate. So once you are very familiar with the bonding number that we see in the periodic table, once you're able to get a hang of the crossover method, generally it will be quite safe. You should be able to do all the chemical formulas. So the question is, how do I know what are all the various chemical symbols? How do I know NH4 is whatever? Okay, all this can actually be found in your textbook. Now I didn't include the textbook page over here. Okay, I didn't include a textbook page over here, but there's one page in your textbook that actually have a list of all the ions. Now I didn't want to include it inside here because it's gonna scare you lah. Walao, you're thinking so many ions to remember, how to remember every single thing. So therefore, I'm not gonna write it all down. The key idea here is use the bonding number. In addition to the bonding number, what I need you to remember is actually hydroxide, carbonate, sulfate, nitrate. So I'm going to write down all the names in red. So this one you all take down. So this is hydroxide. So must know hydroxide is OH minus. This is carbonate. Must know is CO3 2 minus. This is nitrate. Must know is NO3 minus. SO4 2 minus is your sulfate. Plus the last one that we just gone through. Okay, the last one that we've gone through 2 times is actually your ammonium. What is the ammonium ion? It's actually NH4 plus. Okay, sorry, I realized I reversed the color, but you all get a hang of it. Okay, so these are all the polyatomic ions that you need to remember that will be tested in your syllabus. Anything else, they can't really test you in terms of memory work. Okay, so if you're able to do all this, generally your chemical formulas, you're quite safe in terms of compounds. Okay, so what we have settled so far is chemical formulas, compounds. Okay, so we are done with this part. Okay, done with this part. Now, then of course the question is, what if it's just purely an element? It's not a compound. It never bond to any single thing. Okay, what examples of chemical formulas which is just element alone are? Example, sodium. Just sodium like this. What's the chemical formula of this element? So for sodium, you can also for magnesium. So these elements are not bonded to anything. They just say, what's the chemical formula for sodium? So for sodium, it will just be Na. For magnesium, it will just be Mg. Where did I get all this? literally from your periodic table. So for elements, okay, the chemical formula for elements is actually just the chemical symbol of the element. Okay, so just take note of this. To find the chemical formula for the elements is actually just the chemical symbols. Okay, so another example would be what's the chemical formula for iron? So I want the chemical formula for iron, right? Sorry, wrong color again. Let me make sure my color scheme is the correct one. So I want to find the chemical formula for iron. So iron is an element on its own, not bonded to any other thing. Therefore, the chemical formula will just be Fe. Why? Because just the chemical symbol, Fe. Okay, now there are some exceptions. So I'm going to write down this word called exceptions. Except. So every single thing is just the chemical symbol of the element itself, except what I call the H7 elements. What are the H7 elements? I'm going to list them all out using a purple ink on my periodic table. So what are the H7? So those in purple are my H7 elements. H7 elements. What are they? This guy here. Maybe shouldn't do that. See whether highlight will work. No, doesn't work well. Sorry. Maybe use yellow to just shade over. Right, so hydrogen is my first H7 element. So hydrogen, it exists actually as a hydrogen. It will exist as a H2. My second H7 element is actually element number 7, nitrogen. So for nitrogen, it exists as N2. Next, one of the H7 element is oxygen. So oxygen, the chemical formula for oxygen is O2. Okay, I'm going to shade the rest of the H7 element. We got fluorine, chlorine, bromine, iodine, astatine. So you can see H, and you can see this number 7. You can see when you really draw it out, it's actually a number 7. Okay, so what's the chemical formula for the rest? So fluorine is actually F2. Chlorine is actually Cl2. Bromine, Br2. Iodine, I2. And lastly, astatine is actually At2. Okay, so all elements are generally, whenever you write the chemical formula, it's just the chemical symbol itself, except this, what I call the H7 elements. Hydrogen with all of these others here. How do you know what are the H7 elements? Shade this in your periodic table. So you look at the way how I'm decorating a periodic table. So first thing, I always write the bonding number on top. Next thing, I should shade the H7 elements to remind me that these are what I call the H7 elements. Okay? So what I've done so far, I've settled in terms of the chemical formulas for compound, chemical formulas for elements. Okay, so these are the two parts I've covered, and hence you have actually covered most of your chemical formulas already. Now, we're going to go on next to chemical equation. So I spent half an hour in chemical formulas. Most probably I'll spend about another half an hour in terms of chemical equation. Then we will finally move to chemical calculation. Okay, so let's go on next part, chemical equation. Okay, so next part here, we're going to try to understand what chemical equation means. We need to interpret them. We need to understand what it means. So chemical equation that takes place around us, we need a way to sort of like describe what's happening. So you can see that there's two ways to describe it. Methane plus oxygen give me carbon dioxide and water. This one over here, we call it a word equation. Meaning you're using word to describe what's happening. This one over here, we actually call it a balanced chemical equation. So this balanced chemical equation here, you realize you're using all your formulas that you have picked up just now, and you're putting it into words. Okay? Same thing you can see here in terms of photosynthesis. We know the process photosynthesis in primary school. Okay, so how exactly is being written? Most of you will remember writing this out. So what you have been writing is actually the word equation. But we are gonna, because of the level that we are studying in chemistry in secondary school, we will tend to write the chemical equation. Okay, to be more precise, we will write the balanced chemical equation. Now, please don't scare. You don't need to memorize this. Don't need to memorize. Okay, I won't test you. We won't test you this because you're not taking bio. Okay, so don't be scared. Now, so what exactly does a chemical equation tell us? So a chemical equation actually shows what happens in a chemical reaction. It tells us which reactant and products are involved in the reaction. So this is a chemical equation. I draw this dot, 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 okay, and the arrow here, because those things before the arrow, we call them the reactants. Those things after the arrow, we call them the products. Okay, so the things that are reacting, that's why they're called reactants. The thing that's formed, we call them the products. Okay, next, the chemical equation also tells us the relative amount of reactants and products that we need. Okay, in terms of relative amount, we're actually referring to mole. We'll cover it later on. So, but what we also know is that imagine if the formula looks like this, means I need one Fe atom to react with one sulfur atom so that I can get one FeS. So it tells you it's a 1:1:1. Okay, I need one Fe plus one S to give me one FeS. I mean, logic, you all can get it lah. So this one, okay, you should be okay with it. Last one is the physical states of the products and reactants. It's not included here, but this one is actually talking about what we call the state symbols. Okay, whether is it solid, liquid, gas, or sometimes we also see aqueous. Okay, we'll go into it later. Okay, so next part, writing balanced chemical equation. So what we are trying to do whenever we are doing balanced chemical equation, we are trying to make sure that the values on the left-hand side must be equals to the values on the right-hand side. Okay, that's for mathematical equation, right? But the chemical equation is the same. We are trying to make the left-hand side equals to the right-hand side. So let's go further into details. Okay, so this is actually an example of a balanced chemical equation. As I mentioned, draw the dot across the thing. This part here is the reactants, the things that are reacting. This one here is the product, okay, because it's after the arrow. Next, you can see the chemical symbols. Solid, we'll use S. G is for gas, L is for liquid. AQ stands for aqueous solution. Aqueous solution means dissolved in water. Okay, so take note of it. And last one, you can see here we are adding a 2. This big 2 here is actually the balance. Okay, it's actually a number we use to balance. Okay, it's the number for balancing. Number for balancing. Okay, so this is the number for balancing. You can see this big 2 here is also the number for balancing. Is it only we can use 2? No, you can use 3, 4. Really, it depends on what is required for you to write here to make sure that the left side is equals to right side. So question, what do you mean by left side equals to right side? So let's go into this. So example, let's focus on balancing first. I got H2 reacting with O2. I know H2 plus O2 give me H2O. Okay, H2 plus O2. I know hydrogen plus oxygen gives me water. That's why I write H2 plus O2 give me H2O. Because I know hydrogen plus oxygen gives me water. So from the word equation, I convert to the chemical equation. Once I convert the word to the chemical equation, then I start to balance. So look at it here. On the left-hand side, I got 2 hydrogen atoms, H2. On the right-hand side, I got 2 hydrogen atoms, H2. So, okay, good. This is what they mean by balance. The left-hand side must be equals to the right-hand side in terms of the atoms of the element. Next thing, O2 over here, left-hand side, I got 2 oxygen atoms, good. But the right-hand side, I only have 1 oxygen atom. This one not balance. Cannot, So I need to balance it. So what should I do to balance it? Now, You cannot just suka go and put 1, 2 in front here and then say, okay, balance, then I put 1, 2 anywhere, how? So take note, whenever you're balancing equation, you need to write a big number in front of the whole chemical formula. So what exactly are we doing here when we make a big 2? Okay, when we put a big 2 like this, okay, it means that we got 2 molecules of water. And when we put a big 2 like this, what's actually happening is that right hand side, now you got 2 times hydrogen atom, 2 times oxygen atom. So I'll have 4 atoms of hydrogen. I'll have 2 atoms of O. So you look at it, after I put a big 2 in front, it has become like this now. So oxygen is balanced, but hydrogen is unbalanced already. Hydrogen cannot balance, right? When I put a 2 like this. So next, okay, once I put a 2 in front, I realize hydrogen is not balanced anymore. So I need to go and balance this one over here. Okay, so what you realize in the next step, they put a 2 in front of the hydrogen, which then is 2 times 2 hydrogen atom. I'll get 4 hydrogen atom. So now we look at this whole thing together. How many hydrogens on the left hand side? Based on this one, let's look at this one. How many hydrogen on the left hand side? I got 4 hydrogen. How many hydrogen on the right hand side? I got 4 hydrogen. So hydrogen, balanced. Oxygen, how many I have on the left hand side? 2. How many oxygen I have on the right hand side? 2. So balanced. So when you're doing balancing chemical equation, you're trying to make sure that the atoms of each element on the left hand side is equals to the atoms of the elements on the right hand side. Okay, so you say, Cher, why the thing like, wow, must balance here, balance there, like cannot one shot do? Okay, the key here to balance chemical equation is to do step by step. Focus on one element at a time. So if you want to settle on hydrogen first, work on the hydrogen. Then next you go on to the oxygen. So do one at a time. It's actually step by step. You can think of it like macam is a trial and error method also. Where you put a number there, then after that from there you need to adjust another number, adjust until you can get the whole chemical equation balanced. Generally, if you put a few 1 or 2 numbers, after a while it should balance on its own already. Okay, so this is one example. Okay, why I purposely want to do balancing chemical equation? Because as I mark your paper, I realize some of you don't know how to balance. Okay, how to exactly do the questions on balancing equation. Okay, so next one, I want us to look at this one over here. Sodium plus chlorine. So this is actually sodium. Okay, you read our example, sodium react with chlorine to produce sodium chloride. So the word equation we can form, sodium plus chlorine gives me sodium chloride. Okay, so some you say, how they get to this? How they know this chemical equation? Simple. From the word equation, okay, we go convert to chemical equation. So first thing, sodium. What's the formula for sodium? Sodium is an element on its own. It's not bonded to anything. So what we mentioned just now is that when you have element on their own, we just write the chemical symbol of the element. As such, sodium becomes just Na. Chlorine is also element on its own. But, chlorine is one of the H7 element. So if it is a H7 element, can I just write the chemical symbol itself? No. Okay, if it's a H7 element, I cannot just write Cl only. If it's chlorine, because about H7, I must write Cl2. Therefore, chlorine became a Cl2. Next one, sodium chloride. This one is a compound, right? So to do compound chemical formula, how you know sodium chloride is NaCl? It's really because you did this. Sodium and chlorine, once they are bonded to each other, to know the chemical formula, we need to do the crossover method. So sodium is over here. Sorry, I shouldn't use yellow. Sodium is over here. Okay, I don't use purple. Oh no. I use blue. Use blue. Sodium is over here, bonding number 1. So sodium is bonding number 1. Chlorine, what's the bonding number? Chlorine is over here, bonding number is 1. Crisscross, Na1Cl1 As mentioned in chemistry, we don't like to write the 1 there, it's not necessary, so we simplify it to NaCl. So back to the thing here, that's why you can see sodium chloride is NaCl. So once you get a chemical equation, this is not done yet, you need to balance it. So based on this chemical formula, I know that I have what? I draw this dotted line to show the reactants and the products. Reactant side, I got 1 sodium atom, 2 chlorine atoms. On the right hand side, I got 1 sodium atom, 1 chlorine atom. Obviously, you can see the balance for the chlorine, clear cut already. So what I need to do is I need to definitely take 2 times of this chlorine. But how to do 2 times? I need to put a 2 in front of the NaCl. So by writing this big 2 there, I'm actually doing this. So now I have 2 sodium, I'll have 2 chlorine. Chlorine now balance. See, can you see left hand side 2, right hand side 2. So chlorine good, balance. But now I look at sodium, crap. Okay, I got 1 sodium on the left hand side, 2 sodium on the right hand side. So what should I do here? I need to make sure I 2 times here, right? How to 2 times here? I'll make a big 2 in front here. So 2 times the sodium atom. In this case, if I take 2 times of the sodium atom here, I got 2 Na. Left hand side 2, right hand side 2. Yes, it's balanced. So this is how you go about it. And then you can see here the steps that's written. This is actually page 110. Okay, so you realize by doing all these steps, finally, you got a balanced chemical equation. Okay, now, take note, I don't want to focus on the state symbols for now, because it will just add another layer of things to learn at one shot. So I just want to focus on chemical formulas. From chemical formulas, we're going to do balanced chemical equation, full stop. State symbol wise, we'll do another time. Okay, so this is another example that we have done in terms of chemical equation and balancing it. Okay, now this part over here, okay, page 111, okay, I'll leave it to you to try to balance, to look at the solution over here. Okay, I don't want to go through another example already. Okay, because if I spend one more time on this, it's gonna be we won't have enough time for chemical calculation. Okay, so but the general idea I hope you understand is that chemical equation actually tells you what's happening. Okay, so just to wrap up for chemical equation using this, when I got 2Na plus Cl2 gives me 2NaCl. This was the equation that we got after balancing. What this actually means is that I got 2 sodium atom reacting with 1 chlorine molecule. So 2 sodium atom react with 1 chlorine molecule. Okay, this will give me 2 sodium chloride. Can? Okay, so in case some of you wondering, why you this one molecule, this one atom? Molecule, you only use it when you see the bottom number here is 2 and above lah. Okay, atom normally just means that is a 1 over here. There's 1 atom, 2 atom kind of thing. Okay, can? So molecule is only when you got that subscript 2 at the bottom. Okay, so this equation just means 2 sodium atom react 1 chlorine molecule to give me 2 sodium chloride. Okay, so this is what your chemical equation can tell you. And with this chemical equation, then you can do your chemical calculation. Right, so let's go to chemical calculation now. Okay, so this is actually now found on your page, textbook page 118. Okay, I'm going to skip through a lot of all this definition because it's seldom come out, the definitions and stuff. And sometimes the definition can confuse all of you. So I'm just going to jump straight into how to go about doing chemical calculations in terms of mole. So we're going to look at in terms of mole, what is it, how to really go about calculating. So we just jump straight into the solution. Okay, how to go about finding it. Relative atomic mass, forget it lah, don't need to know. Okay, I will later sum up all of this. Why are AR values not whole numbers? Forget it lah. Okay, this one also don't you know lah. Unless when you do Sec 5, then better know all this. But now Sec 4N, it's great. Don't bother. Relative molecular mass, relative formula mass. Wow, why got relative atomic, relative molecular, relative formula, so many relative? Ah, don't bother. Okay. Now, I want you to, in terms of all the relative mass, right? Now, you realize we got this relative atomic mass. We got relative molecular mass. We got relative formula mass. Now, it is going to be very confusing to just know the differences between these three, okay? Because the difference is really quite minute. It's very, very small. And hence, right, I don't want you to confuse yourself all this. Just take note, we just cancel all the middle word. So typically, when you want to find what the mass, right, we use the idea of relative mass. That we're going to term it as, sometimes also known as what we call the molar mass. Okay, these two things, we will term it as MR. So whenever you realize, right, in questions that you see, they always ask you find the relative mass, relative molecular mass, whatever. So we just take it as relative mass. Sometimes it's called the molar mass. It's known as this term called MR. How to find MR is the important thing. How to find, or how to calculate. If you're able to calculate MR, actually we are quite safe already. Okay, so this is where the next part comes in. So I want us to look at this table over here. Okay, how do I exactly calculate the relative? Okay, ignore the word molecular, relative atomic mass, relative blah blah blah. So how to find the relative mass? So now, first thing, chlorine, the formula is Cl2. Cl2 means that there's 2 chlorine in one molecule. So how to find the relative mass? Because I have 2 chlorine, I take 2 multiplied by 35.5. Where did I get this 35.5? Go back to periodic table. All of this periodic table, right? You realize, can you see this relative atomic mass? So what they are trying to say is hydrogen. Each hydrogen, the relative mass is 1. Lithium, can you see this 7 over here? Each lithium, the relative mass is 7. So the bigger number, okay, is always what we call the relative mass. So if you look at chlorine, can you see here 35.5? So one chlorine, the relative mass is 35.5. So if I got Cl2, which stands for I got 2 chlorine, I take 2 multiplied by 35.5, I'll get 71. So the relative mass of Cl2, wait, so let me write Mr of Cl2 is actually equals to 71. Okay. Next, we look at nitrogen dioxide. It's actually made of 1N and 2O. 1N, 2O. So how to find the relative mass of NO2? So the Mr of NO2 is actually equals to 14 because it's 1 times 14 plus 32. How you get 32 is because it's 2 times 16. Where is 14 and 16 from? So look at periodic table. Nitrogen, the mass is 14. Oxygen, the mass is 16. So that's why we got 14, which is the mass of nitrogen. We got 16, which is the mass of oxygen. So 32 here is actually 2 times 16 because of 2 oxygen. And that's how you get 46. If you know how to calculate the MR, okay, actually you can do quite a lot of questions in the thing here. The last one, more cheap one, ethanol, C2H5OH. How to find the MR, the relative mass of ethanol. So to find the MR of C2H5OH, okay, you first need to know is that this is made of 2 carbon, 6 hydrogen, because H5 and OH here, can you see 1 plus 5, so 6 hydrogen plus 1 oxygen. So it's made out of 2 carbon, so at 2 times 12, where I get the 12 from is from here. Okay, where I get the 1 from is the mass of hydrogen, where I get 16 from is the mass of oxygen. So 2 times 12, 24, 6 times 1, 6, 1 times 16, 16. So you add up this, it's 46. So the MR of C2H5OH is 46. Okay, so this is how you go about calculating MR, relative mass. Relative formula mass is the same way of doing it. So I'm not going to go through every single thing. But what is I'm going to do, I'm going to actually give you another example. So one chemical formula is aluminium oxide. Aluminium oxide. Okay, so we know based on the chemical formula is Al, bonding number 3, oxygen, bonding number 2, crisscross. I get Al2O3. So I need to find what is the MR of Al2O3. How to find? MR is a relative mass, right? So I need to know, I know this is made of 2 aluminium plus 3 oxygen. So let's find aluminium. Aluminium is over here. The mass of aluminium is 7. The mass of oxygen is 16. So I need to take 2 multiplied by 27. Maybe we got 2 aluminium. 3 multiplied by 16 because I got 3 oxygen. So I'm going to get 54 plus 48. What I'm going to get is 102. So the MR of Al2O3 is 102. Okay, so knowing how to find MR important. I hope by now you are able to get this ready. Okay, so MR, we are done. Okay, so now, once we know how to find the relative mass, okay, of different substances, we can finally go in to do some what we call the chemical calculation. Okay, so we're going to learn how to find mole. Okay, how to find mole. Now, first things first, how to find mole, we're going to actually use this triangle. So what exactly is mole? You realize, wow, this 6 times 10 power 23, do I even use it? I can safely tell you this. In combined science, okay, in combined science, this 6 times 10 power 23 particles is just to let you know 1 mole has that number of particles. But if you look at all your 10-year series, okay, they don't really test you on the number of particles one. So I don't want to confuse you with this, okay? I don't want to confuse you with this. So I'm not going to go through all this, okay, because it's not really tested. What I want to go through is this part here, okay, molar mass. Now, I just need you to know is this the mass of 1 mole of substance. So I'm going to find the mass of 1 mole of substance. This is actually equivalent to the molar mass. Okay, so example, oxygen is O2. What's the MR of O2? I know it is 2 times 16, so it's 32. What does this 32 means? This 32 actually means that 1 mole of oxygen, 1 mole of O2, okay, this actually means that the mass of 1 mole of O2 is actually equals to 32. I say again, when you say MR of O2 is 32, right? Actually, you're trying to say that the mass of 1 mole of O2 is 32. Okay, based on this, I want you to remember this triangle. Mass of the substance, mole of the substance, MR of the substance. This triangle is the one that you're going to use all the time for your chemical calculation. Okay, this is what you're going to do to find all your chemical calculation. So we're going to be using this quite a fair bit. So now we all know how to find MR. We all know how to find because we can use the relative mass of the atoms and then just, add them up. I think this one you're quite clear on it. But the question is how to use this to find, like your in terms of your chemical calculation. Okay, so I want to look at examples. Let's not go through this page. Don't want this page. Molar volume of gas. Don't want to go through. Okay. This one good. Okay. Now, we're going to do some chemical calculations, okay, from chemical reactions. So this is the next part. We can find MR already right now. Good. Okay. We know how to convert from mole into MR or from MR into mole. Okay, how do I know this? When do you tell me? Actually, I semi-tell you that. Okay, I told you like a little bit. It's actually using this triangle here. Okay, and how did I go about explaining this? I said when you find that the MR of O2 is equals to 32, what this thing actually means is that the mass of 1 mole of O2 is actually equals to 32. Right, so I tried to use this way to try to explain it to you, but even if you don't understand, never mind. Can find MR, can know how to use this triangle to calculate, can already. Okay, so take note that we're going to use a chemical equation to try to do some chemical calculation. So first part here, what does chemical equation tell you, which I already mentioned? It tells you the ratio of the number of moles of the reactants in the products. Meaning, example, 2H2 plus O2 gives me 2H2O, which means that 2 hydrogen gas will need to react with 1 oxygen gas to give me 2 water. Okay? In terms of masses, we don't try to go into here first. I just want you to focus on this. This equation actually tells you this thing. 2 hydrogen react with 1 oxygen to give you 2 water. Okay? So now how to go about exactly calculating? How is my question normally appearing? So I want to look at this. Calculate the mass of the solid obtained when 16.8 grams of sodium hydrogen carbonate is heated strongly until there's no further reaction. So the chemical equation looks like this. Wow, so cheap. Okay, what it means that 2 of this fella, when you heat them up, it will give me 1 of this fella, 1 carbon dioxide, 1 water. Okay, so the question is, what's the mass of solid obtained? I cancel this word solid. I want to find the mass of sodium carbonate obtained. So in this question, they want you to find what's the mass of this thing obtained. Okay, for me to find the mass of this, okay, I need you to take note. In your chemical calculation, you always go from the mass to mole. Then from mole of one substance, so I say mole of A, I will go to mole of B. Then I'll go back to the mass of another substance. You will see this in action, okay? Let me show you how. So this is actually the way that we always do when we do chemical calculation. So first thing, they tell me I got 16.8 grams of sodium hydrogen carbonate. That means I got 16.8 grams of this fella. Okay? What I need to do first, as mentioned, you need to find the number of moles of this fella. So how many moles of this guy do I have? So to find the mole, you can see mass and mole. How to convert is actually using this triangle. Mass, mole, MR. How to convert from mass to mole? You need the MR. So that's for first thing, step 1, find the mole of NaHCO3. Before I can find the mass, before I can find the mole, I need to find the MR. So 23 because 1 sodium, 1 because I got 1 hydrogen, 12 here because I got 1 carbon, 3 times 16 because I got 3 oxygen. What is all these numbers is actually the mass number of each of the element. So when you add them all up, you get 84. Now, this 84 is the MR of sodium hydrogen carbonate. Okay, this is the molar mass. Molar mass, as I mentioned, is just MR. Okay, so how to find the number of moles? So if I want to find mole, this is actually mass over MR. So you can see 16.8 is the mass. The MR I found is 84. So I take 16.8 divide by 84, I get 0.2 mole. So mass over MR, I find mole. Now the question is, I find mole for what? If I got number of mole, what can it tell me? Okay, so for me to be able to do chemical calculation, for me to be able to find out like how much other substance there is, you know the ratio is 2 sodium hydrogen carbonate, give me 1 sodium carbonate. I say 2 sodium hydrogen carbonate, give me 1 sodium carbonate. This 2:1 comparison, you can only use mole to make that kind of comparison. Okay, those of you who are a bit blur on this, don't worry, we'll go through one more example. So I want to finish up on this one first. So once I've found the number of NaHCO3, 0.2. Okay, next thing I can find the number of moles of Na2CO3. Why? Because 2 NaHCO3 give me 1 Na2CO3. So this one, next thing I need to multiply by the ratio, mole ratio. So number of moles of Na2CO3 over number of moles of NaHCO3. I realize it's a mouthful. Okay. So you take the half multiplied by 0.2, you know that the number of moles of Na2CO3 produced is 0.1. So you realize at this step here, you actually multiply by the mole ratio. After that, you multiply by the MR up here. So you realize it's always divided by MR, multiply by mole ratio. After that, you multiply by MR one more time. See over here. Okay, I don't want to go through the rest of it. I realize this example quite jalad because of the hydrogen carbonate, then carbonate. So it's quite a mouthful. So I want to go through a simpler example. Okay, I want to go through a simpler example. Okay, let's use. Oh yeah, tell what, I don't use this one here. I use one example on my own. So for example, the question can go like this. I say 4 grams of hydrogen. Okay, react with oxygen to form water. So I say now 4 grams of hydrogen react with oxygen to form water. Okay, the question is what is the mass of water formed? Okay, what is the mass of water formed? So how to go about doing this? First thing, must have the equation. H2 plus O2 give me H2O. Okay, how do I know? Because hydrogen is H2, H7. O2, oxygen, water is H2O. Balance it. Okay, so it's 2 over here, 2 over here. So this is the balanced chemical equation. Now, I'm going to teach you a little shortcut using this thing here. So first thing, you know, hydrogen given to you is 4 grams. So I want you to write 4 grams over here. So this is mass. Next thing, I want you to write underneath this is MR. After that, I want you to write mole. So there's a very systematic way of doing this whole thing here. Okay. So what are the 2 columns that I'm really looking at is this thing. This is the column because I'm given hydrogen. What do I want to find? I want to find water. Okay. So I want to find the mass of water, right? So I need to use this table over here. So first thing, I got the mass of hydrogen. I know it's 4 grams. Next, let's find the MR of hydrogen. Well, how to find the MR of hydrogen? Hydrogen is H2. So MR of hydrogen is actually 2 times 1. I'll get 2. So the MR is 2. So I know the mass of hydrogen is 4 grams. I know the MR of H2 is 2. So how to find mole? So with the triangle, mass, MR, mole. So to find mole, I will take mass over MR. I'll get 4 over 2. So the mole is 2 mole. 2 mole. Now, from here, let's go to the column that I want, which is water. How to convert? You need to multiply by water over H2. Now, when I talk about this water over H2, right, actually I'm referring to this big number over here, which I call the mole ratio. So water is actually what? 2. Big number here. Hydrogen, 2. So 2 mole multiplied by 2 over 2. Cancel, 1, 1. So 2 multiplied by 1. It means that if I got 2 hydrogen reacting, I will also have 2 water being produced. Again, if I have 2 hydrogen reacting, I also have 2 water being produced. So 2 mole will also give me 2 more water. Okay? Now, so once I know there's 2 more water, how to get the mass? So how to find mass? I actually need MR still. So let's find the MR of H2O. So MR of H2O, how to find? You take 2 times 1, because I have 2 hydrogen, plus 1 times 16. So what you're going to get is actually 18. So the MR of H2O is actually 18. So now let's find the mass of water. So mass of H2O is actually equals to the MR times the molar. So I take the MR multiplied by the mole, which is equivalent to 18 times 2. I'll get 36 grams. So therefore, what's the mass of water formed? It's actually 36 grams. Okay? So this is how you can go about doing the question using this little table format. Okay, so I'm going to give you another example. I'm just going to go through one more. Okay, another example I'm going to give is, let's do this. So I say 51 gram, 51 gram of nitrogen reacts with hydrogen to form ammonium. Okay, so based on this, okay, then my question to you is, how much, well, what is the mass of hydrogen needed for reaction? So first thing, get a chemical equation. So nitrogen plus hydrogen gives me ammonia, which is NH3. Normally the equation will be given to you, so don't worry too much, but I'm just going to show you how to go about balancing and writing the whole thing. Okay, so this is the chemical equation. Sorry, there's no 2 over here. Okay, this is the chemical equation. Now, so let's start the whole thing out. So if you look at it, what are the quantities given to you? 51 grams of nitrogen. So you know definitely you must start from nitrogen. So let's do the table again. Mass, MR, mole. Okay, 51 grams of nitrogen is given to you. What is the mass of hydrogen needed? So you know that you need to come to here. What's the mass of hydrogen required? So I actually don't really care about the ammonia because they never actually asked me to find anything about ammonia. So I just need to focus on the N2 and the H2. So take note, it's always going down and then coming up. So first thing, N2, I don't know, is 51 gram. So next thing is to find the MR of N2. So the MR of N2 is equals to 2 times 14 equals to 28. Okay, 28. Okay, never mind. I change this number, 51, I realize very hard to divide. I change this to 56. Make my life easier, okay? Make my life easier. 56. So 56 grams of nitrogen at the start. Find the MR of N2, which is 28. Let's find the mole. Mole of N2 is equals to, so triangle, mass, mole, MR. So how to find mole? Take the mass divided by MR. I'll get 2 mole. 56 over 28, I'll get 2 mole. Okay, 2 mole. So I know N2 is 2 mole. Now, look at the ratio here. I know that 1 N2 gives me 3H2. 1 N2 give me 3H2. So if I have 2 moles of N2, so imagine if I put a 2 here, how many H2 am I supposed to have? Based on logic, you realize that, okay lah, I mean 1 is to 3. So if I have 2 moles here, that means the mole of H2 must be equals to 6. Because ratio 1 is to 3, right? So 1 N2 will give me 3H3. 1 N2 will give me 3H2. If I got 2 N2, it must give me 6 H2. Okay, so this is actually how you go about doing the ratio. Next, find the MR of H2. H2 is actually 2 times 1, so it's just 2. Then the last part, how to find the mass. So mass is actually mole times MR. Mass of H2 is mole times MR. So I'll take 6 multiplied by 2. I get 12 grams. So the answer for this is 12 grams. Okay, I hope this flow, you're getting a hang of it. So I'm just going to go through maybe 2 more examples. Okay, hopefully it really will fuse into your brains. I'm really going to give you more examples. So instead of writing words, I'm just going to go straight into the formula. Yeah, so just go straight into the equation. So one typical one that we tend to see is, okay, maybe I use magnesium carbonate. You heat it up, you get magnesium oxide plus carbon dioxide. Okay, so one typical chemical equation. Maybe I say at the start, you are given 84 grams of magnesium oxide, magnesium carbonate. I want you to tell me what's the mass of carbon dioxide produced. So I want to find the mass of CO2 produced. Okay, so I know I'm starting from here because 84 grams of magnesium carbonate, okay, is given at the start. They tell me to find the mass of carbon dioxide. So this is my own created question. I want to, from magnesium carbonate, go to mass of carbon dioxide. So before we go in, let's create the table. So start from mass. Second row should be MR. Third row should be mole. Okay, so mass of magnesium carbonate. Next thing, let's find the MR of magnesium carbonate. So this is equivalent to 1 times 24 plus 1 times 12 plus 3 times 16. So yeah, let me write here. 3 times 16. So if you were to press your calculator, this is 24 plus 60, you get 84 grams. 84, sorry, the MR is 84. Now, once I know the MR is 84, then okay, good. Let's find the mole. So the triangle, mass on top, mole, and MR at the bottom. So to find the mole is taking the mass. So let's find the mole of MgCO3. This is equivalent to taking 84, which is the mass, divided by 84, which is the MR. You get 1 mole. Okay, 1 mole. Now, if I got 1 mole of MgCO3, how many mole of CO2 will I produce? So you look at this equation here, 1 MgCO3 must give me 1 CO2. So if I got 1 mole of MgCO3, obviously I'll have 1 mole of CO2. Okay, 1 mole of CO2. Next, let's find the MR of CO2. So this is equivalent to 1 times 12 plus 2 times 16. So what you're gonna get is equals to 12 plus 32, which then is equals to 44. So MR of CO2 is 44. And now we can finally come to here, find the mass of CO2 form. So what we're gonna have, how to find mass? You take the mole times the MR. So mole is 1. Mole times MR. So I know the mole is 1. I know the MR is 44. So the mass of CO2 produced is 44 grams. Okay, so realize this table is going to help you quite a lot to try to get to the answer all the time. But I think if you are able to construct this table all the time in your question paper, you sure can do the mole calculation. Okay, I give you one last example, then I'll wrap up for the night already. So hopefully you can end by 12:30. Otherwise, I think most of our brain are semi-fried area. Okay, last one, let's try, okay, let's try this one. NaCO3, sodium carbonate. I react it with hydrochloric acid. I react it with sulfuric acid. Okay, what I'm gonna get is sodium sulfate plus carbon dioxide plus water. Okay, let me balance the chemical equation. I will put 2 here. It's only put 2 here. Hydrogen, I got 2, oxygen, 2. Yeah, just let me double check. Okay, should be done. Yes. Sorry, this one got 2. Sorry, my mistake. Okay. Actually, no, I don't want this one. I use back HCl, okay? Sorry, everybody. Let me change to HCl. So Na2CO3 plus HCl, give me NaCl. I need 2 over here. I need 2 over here. Okay, so this one good. Okay, so in this question, maybe I will say that, okay, given that I start with 212 grams of sodium carbonate. So I start off, I say 212 grams of sodium carbonate is used. Okay, so I know our mass of sodium carbonate used is 212 grams. Okay, I want you to find for me how much sodium chloride, what's the mass of sodium chloride produced? Okay, so this is my endpoint. I want to find the mass of sodium chloride. So create your table, mass, the first row, second row is MR, third row is mole. Okay, so I got a mass of sodium carbonate already. Next thing, let's find the MR of sodium carbonate. So I want to find the MR of sodium carbonate, 2 times 23 plus 1 times 12 plus 3 times 3 times 16. Okay, so you're gonna get 46 plus 12 plus 48. You're gonna get 106. Okay, that's the MR of sodium carbonate. And now let's find the mole of sodium carbonate. So let's remember the triangle, mass on top, mass, MR, mole. So to find the mole of sodium carbonate, you actually take the mass divided by the MR. So mass over MR, which is 212 over 106, which is equal to 2 mole. So I got 2 mole of sodium carbonate. Now, think about it, ratio, 1 sodium carbonate, give me 2 sodium chloride. If I got 2 sodium carbonate, how many sodium chloride will I get? So actually the mole of NaCl is actually equals to 4 mole. How do I know it's 4 mole? Because from here to here, I multiply by 2. 1 is 2. If I got 2 mole here, I must add 4. Okay, I hope this part here you all start to understand the ratio part. One sodium carbonate, give me 2 sodium chloride. So if based on my calculation, I know I have 2 mole of sodium carbonate, I must get 4 mole of sodium chloride. So now, since I got a mole of sodium chloride already, let's find the MR of sodium chloride. This is equivalent to 1 times 23 plus 1 times 35.5. So this is equivalent to 58.5. Right, 58.5. So once I find the MR of sodium chloride, I found the mole of sodium chloride, I can find the mass of sodium chloride. How to find? Same thing, use your triangle. To find the mass, you take MR multiplied by mole. So 58.5 multiplied by 4. We get 234. Wait, let me double check. You should get 234. So take 58.5 multiplied by 4. Yeah, we have 234. So this 234 grams is the mass of sodium chloride that's being produced. Okay, so once you got a chemical equation, you know how to create this table. You always know it's always moving down, moving to the other side, then coming back up again. And all you're using is this triangle over here, mass, MR, and mole. Okay, so it's not too difficult. You should be able to solve it. So if you want to make sure that you definitely know how to do it, okay, anyway, I'll send the blank notes, all this to you, so don't worry. Okay, you can actually try to do it one more round. I'll give you another equation. Can be maybe potassium plus water gives me potassium hydroxide plus hydrogen gas. 2, 2, 2. Okay. So maybe I'll say you have what's given to you at the start. The mass of potassium is 78. So you're given 78 grams of potassium. What's the mass of hydrogen produced? So this is the endpoint. What's the mass of hydrogen produced? Okay, y'all can go and figure it out. Okay, I want y'all to go and try figure it out. The answer you should get should be 2 grams. Say again, the answer you should get is 2 grams of hydrogen. So you all can go and work it out, the MR, the mole, and then the triangle, you should get mass, MR, and molar. Okay, so go and try to work it out to make sure that you definitely have gotten the idea of how to do the chemical calculation. Okay, so I'm going to stop the recording now. Okay, because this actually marks DNA. Okay, I think you all should do this as your homework, lah. Do this as your practice. Okay, if you can do this, really more or less quite done already. Okay. Okay, so let me stop the recording.